Welcome back. In the second part of today's course session, we are going to look at how linear transformations and matrix transformations can be used to implement an important operation in computer graphics, namely rotations. So before we do that, let's warm up by answering a question. And as usual, I encourage you, even if you're watching or listening to this lecture via the live stream or later on at home on YouTube, to stop the recording, stop the live stream, put your pens and papers out, and try to answer the question yourself. Unfortunately, unlike me, you will not be able to rely on the help of the people here in the lecture room. So suppose I give you two matrices of the appropriate, with the same dimensions, and I tell you that for every vector x, A times x is the same as B times x. You're going to get the same vector as a result, no matter whether you multiply an arbitrary vector x with A or with B. Question: is A equal to B as a matrix as a consequence? Or can it be that you have two different matrices that satisfy this property?
They should be the same.
One of your colleagues here is saying they should be the same. And this is absolutely right. But why? You know, whenever you say, oh, this must be like this, you always have to come up with a convincing answer. Not for me, for you. Okay, your colleague is saying, well, don't we know that every matrix has an inverse? Okay, that would be a good answer if I told you that A and B are square and that A and B have inverses. But what I'm telling you is that this is true even for matrices that are not square and even for those that don't have inverses. So your explanation is spot on, but for a specific class of matrices, namely the square one that are invertible. Okay, your colleague is saying, but can't you multiply by the inverse of x? But you know, x is a vector. Vectors are not square unless they are 1 by 1. And in that case, they are numbers. So again, yes, but in a very, very specific case. So first of all, if I told you that A and B, instead of being matrices, were functions, when are two functions equal? Absolutely. Your colleague is saying when they give the same result for every x. Two functions are equal if they spit out the same answer for all of the possible inputs. That's the only way that they can be equal. So since A and B are matrices, they induce linear functions. And if two matrices actually satisfy the property that B of x is equal to A of x for every x, then the functions that they induce are the same. Okay, we are getting there. Why? Suppose that you want to argue that A and B must be the same matrix. It would be enough for you to argue that these matrices they are equal column by column. So let's look at an example. So let's assume that I have a square matrix like this. That's my A. And that's my B. So we are doing it for this specific case, but the reasoning holds in general. Okay, so what I want to argue, first of all, is that this column must be equal to the red column here. Otherwise, A and B cannot be equal. So why is that? Well, is there some vector that I can use to multiply A with, so that once I multiplied A by that vector, I get AC? That vector should pick the first element, the first entry in every row. So what should that vector look like? A times, hint, it has something to do with the identity matrix. How about the first column in the identity matrix? 1, 0. Now, what is this? Okay, I multiply A by 1, 0. When I multiply, I do it the multiplication for the first row. I get A times 1 plus B times 0. Hey, I get A. If I do it for the second row, I get C times 1 plus D times 0. So I get C. But that's equal to what? To B times 1, 0. Because I'm assuming that AX is equal to BX for every X. So in particular for the vector 1, 0. But what does this do? It picks out the first column of the matrix B, which is EG. So A is equal to E and C is equal to G. Now, how do I figure out, how do I prove actually that also the second column of A is equal to the second column of B? Well, what is the vector that I use to multiply A and B with? Zero, 1. Because 0, 1 is going to pick the second entry in each one of the rows. And since they must be equal, because AX is equal to B of X for every X, so in particular A0, 1 is equal to B0, 1, I also get that the blue columns are equal. But so the matrices A and B are equal. Because they induce the same function, and two functions are equal if and only if they spit the same result for every input that you can possibly give them. And that's computer science. When are two implementations of the factorial function actually implementing the factorial function? When they spit out n factorial for every input n that you can give them as input. That's when you can use one instead of the other. So for functions that are implemented in terms of matrices, the linear functions, checking whether two functions are actually the same amounts to asking whether the matrices that induce them are the same matrix. So function equality becomes an issue of checking for equality of two matrices, which is something that you can write a program for. Whereas for functions where you have infinitely many inputs, it becomes a little bit more complicated. You cannot run them on all possible inputs. There are too many. But the functions are nice and small, or at least nice and finite. 1,000 by 1,000 perhaps is not so small, at least for us humans, but for the machines to do the calculations for us, they are not that difficult after all. Are you happy with this? Sort of. In any event, I encourage you to think about this at home if you don't have anything better to do, which is kind of unlikely, but there you are. So let's get graphical again. What we are going to do now is to look at how matrix transformations can be used to implement rotations. Things like spinning around of Luca by 360 degrees. Okay, so by way of motivation, I've grabbed another one of my favorite comics from XKCD. This is how to implement a matrix transformation that takes me in a normal horizontal state, and after answering 385 messages on Piazza, all asking for the same thing, brings me in horizontal position. This is bound to happen at some point, hopefully not yet, and hopefully not before this course is over. But anyway, sort of why is it, and in what sense does this transformation takes a vector which is horizontal and turns it vertical that way? Well, I hope that by the end of this part of this course session, you will be able to laugh at this very nerdy comic. So if you will laugh, then it means we've been successful. So in order to understand why you should laugh at this comic, what we need to do is to answer this motivating question. Why is it that the matrix like this one, with all kinds of sort of strange symbols in it, perhaps for some of you strange symbols, for some others this will ring a bell, actually rotates this vector and makes it look like this? So let's see. Suppose that I ask you to come up with a transformation, which is a matrix transformation, that maps vectors of size 2 to vectors of times 2, and that rotates points by 90 degrees counterclockwise. So in the opposite direction from the clock. So let's see what this transformation should do. And let's draw. So I want you to implement for me this transformation R90 that takes points in R2, gives us point in R2, and that does a rotation by 90 degrees counterclockwise. That is to say, it goes like this, 90 degrees. So So this is a matrix transformation. So if I want to determine what this transformation is going to do to every point in R2, I need only to focus on how many points. I need to know what R90 does to how many points? 2. It takes 2, baby. As the function, well, not the function. There was a song, I think, at some point that says this. Okay, so in this case, since the transformation is from R2 to R2, it takes 2 points, baby. And what are these 2 points? Think. Okay, so remember, you need to know what the transformation R90 does to the 2 columns of the identity matrix. 1, 0, and 0, 1. So the point 1, 0 is the red point here. The point 0, 1 is the blue point here. And what this transformation does is to rotate this point, move it by 90 degrees in a counterclockwise against the movement of the clock. So where does 1, 0 go if you move it counterclockwise by 90 degrees? It goes to 0, 1. So it goes here. Sorry, change color. That's where it goes. We move it this way, 90 degrees. So where does the blue point go if you move it by 90 degrees against the clock? It goes to -1, 0. So the blue point moves there. So it goes here. So this is the effect that the transformation R90 has. Okay, so it maps the point 1, 0 to 0, 1, and it maps the point 0, 1 to -1, 0. So what is the matrix that implements this transformation? Well, all we need to do is just to use these two vectors that we got. So the matrix that implements R90, let's call it A90. It sounds like a chemical compound, but there you are. It's 0, 1, -1, 0. Yes. Okay, the question is, why can't you use one point and just repeat the function? For this specific transformation, you could, because applying the function to 1, 0 once would give you the other column of the identity matrix, but in general, that's not true. So you need 2 points to determine a transformation from R2 to R2. Good question. In this case, because of the nature of the transformation, it so happens that by applying the transformation to one of the columns of the identity matrix, you get the other column afterwards. But that's just by chance. In fact, very soon we will see that that's not true in general. Okay, so shall we see what this transformation does to a simple geometrical shape? And the answer is, of course, a resounding yes, which I haven't heard, but it doesn't matter. I just answer myself. I'm sort of schizophrenic enough to be able to do that. So let's see what happens. So let's assume that I have these 4 points here. These are the points 1, 0, 2, 0, 1, 1, 2, and 2, 2 modulo things. And we have all the stuff in the middle, all the points in the middle. And now we multiply the corner points of this rectangle by the transformation A90. And let's see what happens. Here we have 1, here we have 2, here we have 1, here we have 2. Warning, drawing is not to scale. It doesn't really matter. So let's see what happens. So I have my matrix A90, which is this one. What happens if I multiply this matrix by 1, 0? Well, we know what happens. We calculated before. This should go to where? 0, 1. Okay, so we get this point here in correspondence of this point here. Okay, what do you think happens if I multiply this matrix by 2, 0? Well, I get 0, 2. I don't even need to calculate it. Why? Because this function is linear. 2, 0 is twice 1, 0. So the result is going to be twice of the result that we just got. So it's going to be 0, 2. So, okay, let me proceed through the colors. This point here is going to go here. Okay, so now what happens if instead I multiply this matrix by the point 1, 2? What do I get? Okay, I get -2, 1. Why? Because I have 1 times 0, that's 0, plus -1 times 2, that's -2, so I get -2, and in the other case, I just get 1 times 1, plus 0 times 2, that's 1. Okay, so it's -2, -1. So the green point here goes here. Fortunately, I have one more color. So where does this point go? Well, you can calculate at home that it will go here. So actually, the rectangle now spans this area, which is kind of what you expect, because if you take this thing and you rotate it by 90 degrees, it will go here. So you just rotate this line here with the figure, and it will now go where this one is. So this works, but this is a fairly simple rotation, 90 degrees counterclockwise. So why does this matrix do the job? Well, because we calculated it. But if somebody says, okay, I want the rotation counterclockwise, but I want you to rotate by 45 degrees. How do you calculate the matrix that does the job? And if instead you were asked 30 degrees, 60 degrees, 75 degrees, 135 degrees, how do you do it? Well, there is a general recipe. Sigh of relief. But what is it? Of course, you can actually do this by composing many simpler rotations, but this is about composition. It's not. So what is the matrix? And that's my question, again, now on the slide. What if I want to rotate by t degrees for some value of t? Absolutely. The transformation is down here. For some mambo jumbo called cos of t and some other mambo jumbo called sin or sinus of t. Now, in Italian, the sinus is called seno, which is also the word for breasts. So you can imagine what kind of reaction one gets in trigonometry classes, especially if you're in an all boys class like I was. And the teacher is a woman. Well, there you are. There you are. Political correctness. But anyway, so why is this the answer? Why is this the answer? And what is this cos t and sin t? Okay? Now, whenever people see cos and sin, and that was certainly my case when I was, after I finished laughing during my first classes, I sort of said, I'm not going to touch this stuff, not even with a barge pole. I don't really understand this stuff. But in fact, it's not so complicated, at least not in this course, because that's the only use we are going to have for this cos and sin. And these are the only trigonometric functions that you will need in this course, and in fact, only today. So let me explain you what this stuff is in one slide. It doesn't take longer than this. Well, we all love circles, isn't it? Well, some of us love them more than others. But here's for you a circle of radius 1. So you obtain this circle by taking this segment of line 1 and by making it go round and round, round and round. Well, actually, if you're good at drawing, it only takes one round. This is what happened to the Italian painter Giotto in the 13th century when he sort of wanted to get a job to design the Tower of Giotto that you can see in Florence today. And they asked him, why are you qualified to do this architectural job? You're a painter. And according to the legend, he drew a perfect circle in one go. And they said, okay, yes, you're qualified. And the thing is still standing now after 700 years and more. Okay, so now suppose the radius spans an angle of t degrees with the xy axis, in particular with the x-axis. Now, what is the cosine of t? Well, this is nothing but the projection, the length of the projection of this point on the x-axis. Whereas the sine is nothing but the projection of this point on the y-axis. Now, I'm afraid you left, I'm not Giotto, and I think this will show. But let's draw, or let's pretend to draw. Okay, so this is my circle. Well, it's not actually, sort of. So this is my radius 1, and this is my angle t. This is my t. So if I project here, this thing here, the length of this is the cosine of t, or cost in this case. That's what it costs. So that's the cosine. So what is the sine? The sine is the projection on the y-axis. So it's this thing. That's the sine. And you know, since the radius is 1, Pythagoras' theorem gives us the fundamental relation between the sine and the cosine. Why? Because here you have a right triangle whose two sides are the sine and the cosine of t, and whose diagonal is of length 1. So Pythagoras' theorem tells us that the square of 1, namely 1, is equal to the square of the cosine of t plus the square of the sine of t. It's all about triangles. And you know what? Now you have everything that it takes to figure out what matrix induces a rotation counterclockwise by t degrees. So let's see. You need to know what this transformation does to two vectors. Who are they? 1, 0, and 0, 1. So let's start with 1, 0. You start from here, and you rotate the green point by 90 degrees. By t degrees, sorry. Where does it go? It goes here. Because that's exactly the angle that we rotate it by. But now, what are the coordinates of this point? One, 0 goes to a point, which is the green point here, whose coordinates are the cosine of t and the sine of t. So these are the first two. This is the first column of the matrix that implements a rotation counterclockwise by t degrees. Okay, the other point that we need to bother about is the point 0, 1. So let me draw, in order not to clutter this picture, let me draw another circle for your visual pleasure. Or, well, perhaps not visual pleasure, but there it is. And it's not quite a circle anyway, but it doesn't really matter. So now we start here. And we rotate counterclockwise by t degrees. That's my t. So where does this point go? Well, it goes here. Now, what are the coordinates of this point? We need to do the projections. We need to do the projections. So now, this thing here is minus the sinus of t. Whereas this thing here is the cosinus of t. You simply just look at this picture that we had here, and you just rotate it. So that's the reason why the second column looks like this. And you know, if t happens to be 90, let's see what this matrix becomes to. And it should become what we calculated before. Now, what is the cosinus of 90? Remember, 90 means you've done the rotation here. So if you are at this point, what is the cosinus of this point? It's 0, because you just project this on the x-axis and you get a point. The length of that point is 0. So you get 0 here. Now, what is the sinus? The sinus is exactly the height here, and it's 1. So you get 1 here and minus 1 here, which is exactly the matrix that we calculated before without any need for any trigonometry. So that's the reason why that matrix is like that. Now, I told you that by this point you will be able to laugh at the XKCD cartoon, so let's see why. before we actually call this a day. What is this matrix? And now you see the matrix next to it. It's the rotation by 90 degrees, but now clockwise. Because the only thing that changes is the minus signs on the sinuses. So if you take the matrix A1, the vector A1, A2, and you rotate it by 90 degrees clockwise, what is it that you get? Well, pictorially, you get this. You put the vector to sleep clockwise, vertical clockwise. So your colleagues now are just laughing in stitches in the room, and I'm sure you're doing the same at home. I still have 2 minutes, but I don't think I can cover very much material in 2 minutes. And since we just had a laugh, this is, I think, an excellent time to take questions if there are any. Otherwise, I just send you to whatever else you were planning to do. So the question is, where would... Okay, so the question is, if you were doing a rotation counterclockwise or clockwise, well, it's the same actually, by 180 degrees, then you would take the cosinus here, the minuses will be here. Because cosinus of 180 degrees is -1, and the sinuses would be 0. Excellent question. Okay, people are already leaving, so let's call this a day.